Hello and welcome to Programming Like It's 1979, NAND to Tetris. This is the lab for the Arithmetic Logic chapter. So let's take a look at what we'll be doing today. We'll be creating 5 circuits. We're going to start with a half adder, move on to a full adder. We're then going to make a 16-bit adder, followed by a fairly trivial 16-bit incrementer, and lastly, we will build a full-fledged Arithmetic Logic Unit, or ALU. I think you'll be surprised at how quickly we're going to move from very simple combinatoric circuits to something fairly sophisticated that's doing real work. So over here we have the HDL definition of our half adder. You can see it's supposed to compute the sum of 2 bits, and we have an interface definition with an A, a B as our in, and sum and carry as our out. Let's flip over to digital, where I've already instantiated the input and output. So one thing I find is that this description of add 2 bits doesn't really give us the full story. In cases like this, I like to look at the truth table. So let's bring that in and take a look. What we can see here is we have 2 inputs and 2 outputs. And if you look at this for a little while, it's very simple. And in fact, if you look specifically at the sum and carry columns one at a time, do you notice any patterns? Well, if we look at, let's start with sum, we could see that when both values are 0, sum is 0. When either value is a 1, either input value is a 1, then sum is 1. And when both values are 1, sum is 0. That should sound familiar. That is almost the definition. That is the definition of the XOR gate. Likewise, if we look at carry, we can see that it's always 0, except when both inputs are 1, in which case it's 1. That's an AND gate right there. So my first instinct at looking at this is maybe we can do this just using a sum for the XOR gate and an AND for the carry gate. Let's give it a shot. I should say, I don't think watching me place components in Logisim is terribly compelling YouTube, so throughout this video, I'm going to use the magic of editing to skip to the end for you. And I'm not going to make a big deal about it. I just wanted to mention that I'm doing it once right now. So here we have a circuit. Let's execute it. We can see both inputs are off and sum and carry are off. As we turn them on one at a time, sum becomes lit. And as we turn both on, sum goes off and carry goes on. That's our half adder. So with that, now we know enough to actually implement our half adder in HDL. We know we're going to have 2 parts. We're going to have an XOR, and it's going to be wired up to each input, and its output is going to be wired up to sum. And the same with AND, only its output is going to be wired up to carry. By the way, all of the projects for this week's lab are in the directory projects02. Name doesn't match the, I think they are capitalized like so. Try that again. There we are. Let's load our test and run it. Let's turn the speed up so we're not sitting here waiting for it. Great, we've successfully created a half adder. Now, one reason a half adder is called a half adder is that it won't deal with carry as an input. To correctly propagate a carry bit, we need what's called a full adder. A full adder, rather than just taking 2 inputs, A and B, takes 3 inputs, A, B, and C. With a 3-bit adder, we can start chaining them together to deal with larger numbers of bits. There are a few different ways to make a 3-bit adder, but the hint I gave you in the lecture for this week suggested using 2 half adders and 1 simple gate. Fortunately, in digital, if we go to the Components Custom menu, we could use any circuit we've already made that's been saved in the same directory. So I'm going to drop a couple of half adders here. There is a way to change these to have custom images for your chips. I just haven't done it yet. So the interesting thing about making a full adder is that although I certainly think of these inputs as being two sums and a carry bit. That's not actually, the circuit doesn't really care, right? As far as the circuit is concerned, it's being asked to add these 3 bits, and it doesn't privilege any of them. So that immediately suggests a solution. What we're going to do is we're going to wire up A to A, like so. We're going to wire up B to B, like so. And from those two, we're going to get a sum. And then we're going to take that sum, and that sum is going to be the new A of our second half adder. And then we're going to take our third bit here, C. We're going to wire that up to B of our second half adder. That gives us a sum output, which is going to go to the sum output of our full adder. That leaves the question of what do we do with these carry chips? Either one of these 2-bit additions could overflow. So if either of them overflows, we want to carry. So we're going to take an OR bit here. Excuse me, we're going to take an OR gate here. We're going to wire that up like so. And we're going to, at this point, we should have a working circuit. Now, how do we test this circuit? Well, we could mess around with the inputs. The truth table for a full adder is actually a little more complicated than for a half adder, so I'm not sure I want to sit here and flip through each. Let's spot check a couple of these. So let's take the case where everything is turned on. We expect both sum and carry to be turned on. That's correct. Let's take the case where 2 of them are turned on. Carry is on and sum is off. That's correct. And that should be true no matter what we do. Whichever 2 of these are turned on, that should be true. That looks okay. Let's go ahead and try it in the hardware simulator where we have a full test suite that will try every case for us so we don't have to. So summarizing before we go to the HDL, we have 2 half adders chained together whose sum output goes to the sum output of the full adder chip and whose carry outputs are ORed to the carry output of the full adder. We're going to wire up the first half adder. Its sum is going to be called, let's call it HA1 sum, and its carry will be called HA1 carry. We have a second half adder, and I think I got the capitalization wrong on that first one. Its A is going to be HA1 sum, its B is C, and its carry we will call HA2 carry. We need its sum output, which is going to be sum equals sum. And then lastly, we need an OR gate. Its A is HA1 carry, its B is HA2 carry, and its output is carry. Well, hopefully I got all of the interface names there correct. Let's take a look. Run the tests. And we're good. Now we've got a full adder. We're starting to cook with gas here. Next, we're going to do the 16-bit version of the full adder. As I alluded to in a previous video, diagramming things with this many bits can be really annoying. You have a lot of splitters and a lot of mergers. So while I am going to do that for the ALU and the CPU, for this one, let's just do it in HDL. We can see here we have 16 bits of input from A and from B, and then 16 bits of output from the same. All we need to do is chain together a bunch of full adders so that the carries cascade to the end. Most importantly here, note that our specification tells us that we are allowed to ignore the most significant carry bit. So if we do an arithmetic operation that overflows a 16-bit value, we're going to give the wrong answer. Let's start typing. We're going to use our bus syntax to get the correct wires here. Now, for the first full adder in the sequence, there is no carry. So what do we use for the third input? In this HDL language, we could use the keyword false, which means that this input C will always have the value 0. In fact, we could have used a half adder for this chip instead of a full adder for this very first one in the sequence. It would use a few fewer NAND gates, but for simplicity's sake, I'm just going to continue to use full adders all the way down. So now we need to do our second one. And here we are actually inputting, we are actually carrying over the carry from our first full adder. So we're wiring that up to C, and this one's carry is going to get a new wire. And then we're just going to do this 14 more times. And we're back, having copy and pasted a lot and changed the number of numbers and reformatted the code to fit the screen a little better. What you can see here is that we are cascading the carry through all of these adders. So this adder here sends its carry to FA5 carry, and then the next adder in the sequence takes that carry in. And then the last carry in the sequence, we just connect the wire to false and ignore it. I should say this is not the most efficient way to create a multi-bit adder. You might already see the problem, which is that as we add bits, we're increasing the length of this chain of connected adders, which means that you won't be able to get an answer to your addition until all the bits propagate through all of the adders, which, as you could imagine, if you're doing 64-bit arithmetic, that's going to add up. We're not going to worry about the efficiency issues here. Let's go ahead and jump over to our hardware simulator, load the chip, load the script, and run. Oh, we've made some sort of mistake. Well, let's take this moment and try to figure out what is our mistake. So if we look here, we're being told there's a comparison failure at line 3. The highlight here is a little bit misleading. What we actually want is this comparison here, the comparison before the highlight line. We can see that A has been set to all zeros and B has been set to all ones. So somehow a pretty simple addition failed here. So how do we know how it failed? Well, if we look at different parts of our code, as we click around, the state of the internal pins is shown to us. But this is still pretty hard to interpret. But if we look up here at the output, we can see that there's a value. And we see that value is -4097 decimal. I don't know what that looks like in binary. Fortunately, if we go up to this format pull down, we can change it to hexadecimal or to binary. And in binary, we know that this arithmetic, the answer should be all ones for this addition. We can see it's 1110. So our fourth from the end of the chain, we got something wrong. Let's go back and look at our code. And let's count back. 1, 2, 3, 4. And right there, we can see there's a discontinuity. I think that I actually am missing 2 lines here. So let me go ahead and fix that. And now hopefully we've caught all of the errors. Let's go find out if there are others. Reload the chip. Reload the script. And this time we have a working 16-bit adder. Is there a lesson here? Yes, there is. It's always write tests. And if you have tests, use them. Our next chip, and our penultimate chip for this lab, is the 16-bit incrementer. Fortunately, a 16-bit incrementer is really just a special case of a 16-bit adder. The specification is here. Output equals input plus 1, arithmetic addition. You can see we have an input and an output, and that's it. Well, let's go ahead and put our add 16 chip here. The input is just going to be the input. The output is just going to be the output of our adder. And that leaves us with the question of, well, what do we put as the input to our B here? Well, I don't think I can just give a constant. I don't think this HDL language understands it. But you know what? Let's see. Maybe that works, and I'm just unfamiliar with the specification. a pin name is expected. All right. I think what we might be able to do here is use the bus syntax to specify that pin 0 of our B input gets a true value. Then we can possibly specify that everything else gets false, or we could just leave it unwired. I don't know if that would work. Let's find out. So we're going to say B0, our least significant bit, gets true. We're going to say that B1 to 15 get false. Will that work? That might work. It didn't complain about the syntax, so that's great. It worked. So there you go, the power of bus syntax. That's our 16-bit incrementer. All right, you've been waiting for it, the arithmetic logic unit. Everything we've done up till now has been a precursor, has been just a warm-up exercise. The ALU is the first truly complicated piece of machinery that we're going to build. The ALU is complicated. It computes any one of a number of functions. I'm not going to read them all here. X plus y, x minus y, y minus x. A few constants such as 0 or 1 or -1, addition, subtraction, x plus 1, x minus 1, some bitwise operations like x and y or x or y on 16-bit inputs. And it does all this based on 6 input bits. How do we do that? Well, we can see that here's where the effects of those input bits are described. So we have this ZX bit. If the ZX bit is true, then whatever the caller into the ALU provides as the X value is ignored. We throw it away and we set X to 0. We have a negate bit, NX, which is going to negate it. We have similar bits, ZY and NY, to 0 or negate the Y input. We have a F bit. I think of it as the function bit. If the function bit is true, we're computing x plus y. If the function bit is false, we're computing x and y. And as I said in the lecture notes, these things happen in sequence. So if I say we're computing x plus y, but the zy bit is set, then we know that by the time we reach the kind of core function, we've already thrown away that y value, and we're actually computing x plus 0. So logically, to take this as an example, if zx is 1 and f is 1, all other things being equal, if all other bits are false, I would expect that to be return the x value. So let's take a look here. Here's our actual interface specification. We have two 16-bit inputs. We have our 6 flags, and then we have 3 outputs. One is our output, the actual result, arithmetic result from the ALU, and then we have these 2 things that I think of as flags. One of them is 1 if the output is 0, so a 0 flag, and the other is a negative flag, NG, if the output is less than 0, the NG flag is high, otherwise it's low. We got our work cut out for us. We could just dive in and try to do this via HDL, but this one I feel like this one is worth it to try and diagram. Let's dive in and see if we can do it. So the hint that I gave you in the lecture notes was to think about sequencing. So these are our inputs and outputs for our chip. I don't actually know if I'm going to have enough space here to diagram this comfortably, but let's take a look at it. So we have these 6 flags here, and these 6 flags all operate at different, I hate to use the word times since this is a combinatoric circuit, but I'm going to do it anyway. If we think of the data flow of this chip as going from left to right, these Z and N flags, the 0 and negative X and Y, will be applied first. In fact, they're going to be applied in a, does it matter if they're applied in a specific order? No, because we can negate 0 and that's not going to change it. Then, after these flags have been applied conceptually, then this function flag gets used. and is going to decide whether we're doing AND or addition. And then lastly, we have this NO, negate output flag, which is going to decide whether or not to negate the output. So that suggests some layout, and I find that adjusting the layout is helpful. Give ourselves a little more room. So what I'm going to do is I'm going to take this negate output flag. I'm going to put it very close to the output, just because I suspect that whatever we need to do, we're going to need that flag nearby. We'll rotate it south so that it's giving us a bite at that apple. And this F flag, I keep drawing wires when I mean to move things. This F flag is probably going to be somewhere in the middle here. All right, so what next? Well, we could approach this two ways. We could work from the inside out and work on the core of our logic, or we could work on manipulating these X and Y values. I kind of like the idea, because this F flag occupies such a central place in the circuit. I like the idea of asking ourselves, well, how does that work? Plus, it's a single flag, so we don't have to worry about the interactions yet between these other flags. So let's think about that. So we know that there are two functions that F is going to decide between. Looking at the spec again, it's either X plus Y or X and Y. So that suggests we're going to need two different components. First, we might have an adder. That's going to be our X plus Y as one possible component. And second, we might have a 16-bit AND. That's our other component. So that needs to be a 16-bit AND with two inputs. So whenever we're thinking about selection or choice in the context of a combinatoric circuit, we know that we're thinking of either a mux or a demux, right? So which of those makes sense in this scenario? Well, we have two inputs here, and using a demux, which would take multiple inputs and send them to a given output, actually gets tricky if you have multiple values you're juggling here. So I think the thing I want to do is, since I'm not concerned about any kind of efficiency, I want to always be computing both X and Y and X plus Y, and then I'm going to use this F flag to select between the results. So if we imagine our sum coming out of this 16-bit AND, 16-bit addition, and coming out of our 16-bit add, we've got this F flag hanging out here. Let's go ahead and rotate that so it's pointing north in our chip. And let's get a mux. I'm going to put that right here. We're going to make F the selector for the mux. We will say that the first input to the mux is, nope, I got that wrong, didn't I? Let me look at the spec again. If F is 1, then we're doing addition. If F is 0, we're doing the AND. Whoops. Let's flip these. Move this one down here, this one up here. Our AND is input 0. Our addition is input 1. Like so. And that, I believe, is the very core of our ALU. Well, simplifying this worked so well, focusing on the thing where we only have one flag, that I kind of want to do it again. I'd like to do it with our NO flag, our NO control bit, and decide whether or not we're going to negate this output. So here comes this output coming out of our function. And we've got, I think we can do the exact same thing with a different plexer. We can always compute the negation of this output and then use the NO bit to decide whether we use the negation or the straight value. So we know we're going to need a mux, but we're also going to have to do arithmetic negation. So how are we going to do that? Well, in 2's complement, to negate a number, we invert all the bits and add 1. We made gates that do these things. We have a 16-bit NOT gate to invert all the bits and a 16-bit incrementer to add 1. In this case, since I didn't create a 16-bit incrementer in the diagramming program, I'm just going to use an adder to represent that and add a constant value. So in the case where the negate output flag is off, we are going to take just the value coming out of the function mux. In the case where the negate output flag is true, we're going to pipe it through this not adder chain. And that is the output part of our ALU. All right, let's next go on to the control bits at the entry points of our CPU. To make sure we're doing this right, let's take a look at the spec. So we're going to deal with these 0 bits first. If Zx is 1, set X to 0. And if Zy is 1, set Y to 0. All right. So if Zx is 1, we've said that word if, that immediately should suggest a multiplexer to us. Let's go ahead and place one. And I'm going to move our Zx control bit up here so that it's a little closer to the plexer. Hook it up. If Zx is 1, then set it to 0. So that's going to be this input here. This input on the bottom of the plexer is the second input. And we want to set it to 0, so we're going to grab a constant value and put it right there. Let's see. I need to change it to 16 data bits and a value of 0. And that reminds me, the plexer also needs to be, the multiplexer needs to be 16 data bits. Then our X can come in right here. And that's our Zx control bit. So Zy is going to look very similar. In fact, it's going to look identical, except it's going to be dealing with Zy. So I'm going to copy our plexer. We'll put it right here. Try and make it match up as much as I can. Y is going to go there. Zy is going to go here, and I have to rotate it. And I need a constant value. Oh, and I just placed a value, or just placed a wire. Fine, I'll place a new one. I'm reasonably sure there must be like some correct zoom level to be editing these at that makes it less likely that I'm going to accidentally drop a wire instead of grabbing a component to move it. All right, that's our 0 control bits. Simpler than I thought it would be. Let's go on. We're going to do this NX and NY control bits next. Again, let's look at the spec. If NX equals 1, X equals not X. Not X. So that's interesting. I think I have been referring to this NX bit throughout this lesson, or throughout this lab, as the negate bit. And I've been thinking of that as arithmetic negation, in the sense of if the value is 5, then negate it to be -5. But when we actually look at the spec does not say that. The spec says this is a bitwise NOT. So that's good news and bad news. It's good news because that's much simpler than arithmetic negation. It's bad news because I made the same mistake here where we're dealing with the NO flag and negating the output. I made it an arithmetic negation and not a bitwise negation. So before we deal with these two flags, let's go back here. Is this a 16-bit not here? It is. All right, so this is actually not that hard to fix. All I need to do is to remove this adder from our circuit. That goes away, and then this goes there. All right, we just reduced the NAND count in our circuit very easily. And now we're going to deal with these NX and NY control flags by literally doing the exact same thing we're doing here. And we'll put it, sure, we'll put it there so that it can feel like it's in sequence. So this value from X is going to be the first input into our mux. We're going to grab a 16-bit NOT gate, which this one is. Eep, I just broke it. I ruined it all. I'm going to put that NOT gate right there. This is going to come down right here. Grab our control bit, put it there. Once again, I like rotating these things. You don't have to. As we've established, you don't actually have to draw these at all. Now that we've got that, I can grab the whole little complex, copy paste it, put it there. Y goes there. Y also goes into this NOT gate. Move our control bit, and let's rotate it. I think that's correct. So now we have a small complex of wires that handle the ZX, ZY, NX, and NY bits. Let me give us a little more space here. So just to make things a little neater, let's use some tunnels for this next section. I'm going to grab a tunnel, which is going to go right there. And I'm going to name it Ready X, telling us that we've now done all the pre-processing on X here. And I'm going to grab a second tunnel and put it right here. We're going to call it Ready Y. No, I don't want to rename all of them. I just want to rename that one. Then we're going to copy this tunnel and put it here. And we're going to flip it 180 degrees. Great. That's a little too far. Put it right there. We'll do the same with Ready Y. So the only reason I'm doing this is to show off it as a useful feature and also a concept called a net. The idea here is that this wire is going somewhere. We call it a net, which I assume is short for network. I don't actually know that. And so a wire goes in here to Ready X. It will seemingly come out of any other place labeled Ready X. That just lets us avoid stretching long wires across the entire schematic. In this case, they actually didn't have too far to go, but I'm going to use them for the next section. So I wanted to go ahead and use it here. So each of these gets hooked up. Oop. Okay, well, given that I was trying to make this neat, I kind of didn't do very well, but that's fine. The carry bit the carry output can be ignored, I'm pretty sure. I do have to have something wired up to our 16-bit adder, the carry input of that. So I'm just going to grab a constant value and put it there, and it's going to be, I'm going to set it to 0. Let's use our newfound tunnel knowledge to shorten the distance so that we're not dragging a wire. Let's call this true. No, I don't want to use the word true. Let's call this ready out. We're going to copy that, paste it down here. Let's give ourselves lots of room. So let's look at the spec, learning our lesson from having misread the other ones. If out is 0, set the ZR flag to 1. If out is less than 0, set the NG flag to 1. So out of those two conditions, neither is hard, but the NG flag is going to be the easier one. So let's do that first. In particular, what we're going to want to do here is we are going to want to grab the most significant bit from this 16-bit bus coming out of ready out here. And we can do that with a splitter. So let's go grab a splitter. And we'll put it right here so it's nice and close. And we're going to configure this splitter. As input, it's taking 16 bits, and as output, it's going to output 2 buses. One of them is going to have 15 wires, which we're going to ignore. And then the 16th wire is the one we actually want. So we're just going to go ahead and route this that way. And then this is a straight shot right there. And that, I believe, that's the NG flag. We're just literally looking at the most significant bit. Since we're using 2's complement arithmetic, if the most significant is 1, we know the number is less than 0. We're almost there. Let's look at the ZR flag next. So we've got a number of bits coming in our 2's complement representation. If it's all zeros, if every bit is 0, then this flag is high, and in every other case, this flag is low. So we actually made a component that will deal with this. We made an OR 8-way gate. Sadly, this is 16 wires, not 8. So we will have to split this out a bit. And this bit is not fun to draw. Well, let me just go ahead and put these down. You don't want to watch me fiddling with the wires. I'll see you in a moment. All right, now we've reduced these 16 bits down to 2 bits. We take an OR gate, reduce those 2 bits down to 1 bit. If that 1 bit, if any of these bits is on, then this will be on, which is the opposite of what we want. So we therefore grab a NOT gate, a 1-bit NOT gate, and reverse it. And that should be our ZR flag. Run the circuit. It looks like, well, I have everything connected correctly. I don't know if I've done it all in the right order. Let's take a look. 0. We'll set this to 0. We'll leave all these flags off for right now. This is off. That means this is 0 and 0. Our output is also 0. The 0 flag is high. The negative flag is low. That's good. 0 plus 0 is 0. Let's change these values to 1. We'll do some simple tests. Our negative flag went low as soon as we set a value to 1. 1 plus 0 is 1. 1 and 0 is 0. 1 plus 1 is 2, right there. That looks good. Let's make it negative something. Let's do 0x f a, whatever that is. That's an and that's 0. A plus 1 is AAAB. That sounds correct. And the negative flag is set. So this is looking pretty good in our diagram. That said, this is not the assignment. All of that we've been doing here with drawing this somewhat complicated schematic has all been a prelude to actually writing the HDL. Let's go actually write some code. All right, let's get to work writing some HDL for our arithmetic logic unit. Let's start at the entrance, the inputs of the chip, and work our way forward and through to the outputs. So the first flags we encounter are these ZX and ZY flags. Let's handle those first. And how you structure this is entirely up to you. The HDL it doesn't care. You can put these things in any order. You could refer to wires before you've defined them, as long as you define them somewhere inside the body of this chip ALU block. But I'm going to try and keep it fairly straightforward. So let's say ZX and ZY flag handling. Put a comment in. So looking at our diagram, first we need a mux. That's going to be a mux 16. We know that the selector bit is going to be ZX. We need a fancy name for the wire coming out of this. I'm just going to call this XMux out. No, but XMux is fine. Our input is going to be the 16-bit XBus itself. And then for our second input, we need a constant value. We need a constant 0. How do we get a constant 0? We use the constants true and false. I think what I want to do here is, I don't know if I need to define this as a bus, but it should work. I think I could just say B equals false, but let's be explicit that we want all 16 wires set to false. I think that'll work. We'll find out when I load it, when I load the HDL into the simulator if I've made a mistake. And then let's do the same thing for our Y input. Making sure to change all the flags and all of our network names. All right. So that is our X and Y, ZX and ZY flag handling. Next, we need to handle the NX and NY flag handling. I know they're not really capitalized, but makes it easier for me to tell what I'm doing. So here we need another mux, and we also need a 16-bit NOT. We're going to need both of those at all times. So let's say 16-bit NOT. The input here is going to be the output of our XMux. And what we're getting out of here is what on the diagram I called the ready value. No, it's not. Our output is going to be NOT X from the NOT gate. And then we're going to add another mux, another mux 16, and that output is what I had referred to as ready X, meaning all of the pre-processing has been done before it's going to go into our function. Our selector here is NX. Our second input is NOT X. And our A is XMux. The common mistake you might make when writing this HDL is to think, well, my A is my X value. But X value very specifically refers to the value, the signals coming from the X input, which we have already possibly changed. So we need to make sure that we handle that appropriately. We'll do the same thing for the value coming in through Y. Make sure we change the selector, make sure we change that output. So if I've done my job correctly, this is now the upper left-hand portion of the diagram sorted. These things all feed into the F control bit, or the functions controlled by F. So again, we're going to need a mux, we're going to need a 16-bit AND, and a 16-bit adder. So let's put the AND down first, AND 16. It has two inputs. Those inputs are ready X and ready Y. The output we can call AND out. Keep it simple. Then our adder, our add 16, is going to look extremely similar because it has the same inputs and outputs. Add out. These two outputs go into a mux, a 16-bit mux. Let's go ahead and just make those A and B. Make sure if I got that right. Yes, well, let's look at the spec. When in doubt, look at the spec. X plus Y if F is 1. So therefore, the adder is the B input as it is on our diagram. And our selector is F. And our output, we'll call it F out. All right, that's the center portion of our ALU done. And I want to be clear, I want to take a moment to kind of call out, if we had sat down and tried to write this from scratch without having the diagram, different people learn different ways. Maybe there are people who can just kind of blot it all out. I find that having a visual reference really helps me. You should do whatever works for you. If you can approach this purely in code terms, knock yourself out. I find that having the diagram and having the code, even when I don't need the diagram, they provide cross checks. As an engineer, one thing you're going to find is we are human. We will make mistakes. It's why we have test benches. It's why we have test suites. It's why we have references. So merely having these kind of two separate implementations and different ways of testing will help you catch places where you made a mistake. I've made tons of mistakes during this lab, and I've gone out of my way to not edit them out, or if I do edit them out, to kind of call out after the edit, oh, I screwed this up, I wired this over here. And part of that is because I want you to understand that, and I want everyone to understand that making mistakes and learning from them is absolutely part of the process. All right, sermon over. Looking at our F out, we can see that goes to another mux in two ways. Once through a NOT gate. So let's call this our NO flag handling. And we've got a NOT 16, not a NOT 6. This is not tops 20. F out, we'll call this F not out. That's going into a mux with the A input to the mux being F out, the B input being F not out, our selector being NO, and the output being, I think I called it ready out on the diagram. So that, no, I don't actually need, so this is where it gets a little bit interesting in terms of HDL. So we want to do three things with this output. First, we want to wire it up directly to the output of the chip. So we could just do that. Out equals out. And now that out value should be correct. But we also want to take parts of this signal and route them to our flags. And we can do that all on one line here. This is all detailed in appendix, I think it's appendix A of Nissen and Schocken, that covers the HDL language specification. So we could say we want the most significant bit of this signal, which is the 16th bit. It's zero indexed array, therefore it's 15. We can say out 15. This is the 15th pin of the mux's out. We can say that equals, I'm going to call it NG. Yeah, we can just say out equals NG. Now we're going to wire that 15th pin up to the NG output on this chip, this NG here. Then we still need to do this processing for the ZR flag. So I'm going to just add some more directives here. We're going to say the 0 through 7 pins are going to be ZR low, and 8 through 15 are going to be ZR high. Is that correct? I think that's correct. We'll find out. I know the syntax highlighting looks very suspicious here. I'm pretty confident that's just a mistake in a bug in the editor, not in the HDL I've written. All right. So that handles NO and NG. I called that a flag. And then our last little bit here is the ZR flag. All right, so what are we going to do here? Well, we've got these two now 8-bit buses, ZR low and ZR high. So I think what we want to do is we want to put in 2 or 8 ways. Let's handle the first one first. Yeah, it's essentially taking one 8-bit value. I think that will actually work. And we'll call this OR1 out. And then I need a second one of these, which will take a ZR high. I had to think for a moment like whether I was going to have to split this up into 8 separate pins. And I don't think I do. If it turns out I do, well, I'm glad I just gave a lecture about making mistakes. Okay, then we just need a normal OR gate. Normal. We need a 2-bit OR gate. And call that OR3 out because I'm boring. And then lastly, we need a plain old 1-bit NOT gate, which is going to take OR3 out and wire that up to ZR. My belief is I may have made a mistake, I may have typos, but this feels pretty close to me. Let's find out how I did. We'll load our ALU chip. This will find any syntax errors. No syntax errors, that's always a good sign. We load our test and we run it. Wow, I am really happy that that worked out. I probably have implemented various ALUs multiple times, and I usually make a mistake. This time, I think I made the mistakes early enough and managed to catch them. But the thing you want to look at here, if you do encounter a problem, the 2 things you want to look at are, 1, as you run the tests, if you get a comparison error, let's say you'll get a comparison error here, typically you want to look at the stanza before this yellow line, because it will evaluate this output and then move the yellow line and complain about it. And really it means it's this stanza here if the line is here. To actually figure out what went wrong, a good starting place is to look up here at the output pins. Do remember the trick of changing the format. Use whatever number format works well for you. In the case of an ALU, having it in a binary format really helps. And remember that this will show you the state of all of your internal pins. Any name you defined while doing this should be in this internal pins panel, and you can inspect the state of those, and from that, hopefully figure out where you went pear-shaped and correct it. Well, I hope you've enjoyed this. The ALU is a taste of the complexity that we're going to get in the CPU. They are fascinating bits of machinery. My favorite ALU story is that the 8-bit ALU inside the Z80 chip, which is a classic 1980s chip used in many computers and many arcade games, is in fact 2 4-bit ALUs kind of taped together with spit and baling wire. It's a very clever design. Well, I hope you've had fun following along. If you've stuck around to the bitter end, please talk to us in the comments. Tell us how you did. Tell us what tripped you up, what you found easy, what you found hard, what you found interesting, and what you found boring. This has been Programming Like It's 1979. Thanks for watching.